Hello, Mr. and Mr. Ryan, right?
Yes.
What combination? We talk about that. C, 3, 2. 3 apples, picking 2 apples. How many ways? 3 apples. 3, yes. So 1, 2, 3, yeah? Picking 2. 1, 2, 1, 3, 2, 3. That's it. Okay?
And 3, 1, 2, 1.
Okay. 3 apples, picking 1 apple. How many ways?
3.
3 ways. Okay? 1, 2. When you pick 1, 2, you have 3. When you pick 1, 3, you have 2. When you pick 2, 3, you have 1. Okay? We talk about that, right? Combination. The items without orders. Yeah. Picking 2 apples out of 3. We just pick it and we don't need to worry about the order of the apples. But if we want these 2 apples to be different with the sequence, right? 1, 2 is different than 2, 1. Then all we have to do is use this P, permutation, right? 3 apples, picking 2 apples, but 1, 2 is different than 2, 1. Then we have to times the factorial, am I right? Is C, first of all, we pick 2 apples out of 3, and then we permutate, do the full permutation on 2 apples. And we know full permutation of n is n factorial. The first one we have n choice, the second one we have n minus 1 choice, the third one we have n minus 2 choice, etc. till the end. So Pnn is n factorial. Okay, so this combination, we talk about this combination a little bit on day 93. Yeah. Today we're just going to review it and with and a bit extra details. So how do we calculate Cm out of n? How do we calculate this number? Okay, so I give you a hint, alright? So we can think of it recursively, dynamic programming. How? Look, I have n apples. N apples. Okay? And I want to pick m. Okay, so let's take a look at this one. How many choices do we have for the first apple? How many choices?
2.
Yeah, what are those?
Pick it and not pick it.
Well done. Okay, pick it or not pick it. If we pick it, how many apples left? N minus 1, yeah? If we pick it, we have n minus 1 apples. But how many apples we need to pick? If we pick 1 apple already. If we pick this one, how many apples left? We need to pick. No, n apples. And we want to pick m apples. Pick n apples. Okay, so you say the first apple we have 2 choices. We can pick it or we don't pick it. When we pick it, we pick 1 apple. We want to pick m apples. When we pick 1 apple, how many left?
N minus 1.
We have n minus 1 apple left to pick. And how many apples we need to pick from? N minus 1. Right? Because we pick 1 and yeah, there are n minus 1, right? Okay? If we skip it, how many apples left? We need to pick still pick m. How many apples we need to pick from? Look, we skip this one, and how many apples here?
N minus 1.
Yeah, here is n minus 1, right? So it's C n minus 1. We want to pick
M.
m. Wait. Cnm equals Cn minus 1 m plus Cn minus 1 m minus 1. Right? This is how we get this recursion relation for the combination. Okay, let me repeat this. We have n apples. Let's look at this first apple particularly. If we pick it, we need to pick n minus 1 more from n minus 1 apples. If we skip it, we still have m apples to pick. Right? And from n minus 1 apples, right? Because you said 2 choice, you can't eat it. You pick it or skip it, you don't eat it, okay? There are n apples. How many ways to pick n apples? There are 3 apples. How many ways to pick 3 apples?
1.
There are 3 apples. How many ways to pick nothing?
1.
Yeah, 1. Okay, we talk about that. Cnm equals Cnm minus m, right? Yeah? Picking 2 apples is the same as picking 1 apple. Picking 1 apple is the same as picking 2 apples. Cnm equals what if m bigger than n? Right? There are 3 apples. I want to pick 100 apples. How many ways? What should I put here? When m bigger than n, what's the answer?
0.
0. Well done. Because they're impossible, right? Yeah. 0. Okay. Define C and m. If m bigger than n, return 0. If m equal than n, return 1. right? If m equal 0, return 1, right? We talk about it. And otherwise, return c n minus 1 picking m apples plus c n minus 1 picking n minus 1 apple if we pick it, if we skip it. Okay, we talk about it. Easy, Python code. What's missing here?
Cache.
Cache. Without the cache, the time complexity will be very complex, will be exponential because these intermediate values are calculated over and over again. We need to use the hash table or the cache, simply cache to store the intermediate results, okay? This is the dynamic programming, top-down dynamic programming. Any questions on this bit? We talk about this on day 93. Recursion, this is recursion. CNN cache. 1, 1. What's this? Do you still remember it? Look, this value, any value, this value.
Something begins with P triangle.
Pascal Triangle, look, yeah? Look, this value is the sum of the value above, right? C, this is Cn,
Yeah,
M,
but why is it above and it's diagonally left?
right? If you tilt the triangle this way, right? If I write it this way, the number is equals to the numbers above it. But why I write it this way? Because in computer science, the rectangle, the square, match it. Pascal triangle. So this is Pascal triangle. Look, I want to calculate CNN here. It's a sum of Cn minus 1, m, Cn minus 1, m minus 1. Right? Any number is equals to the sum of the numbers above it, two numbers above it. Top down, we use the top down, right? Cn, we want to calculate Cnm. Then we need to know Cn minus 1, m, and then Cn minus 1, m minus 1. Right? And again, this will be spawned into 2. Right? So we have to remember the values. Right? For example, somewhere here, this value could be the same as this one. And then if we spend huge amount of time in spawning the trees here, there's no point to do it again when we need it the next time. So we use the cache. Okay. The other way is use the bottom up. Yeah? We talk about the top down. This is top down. We want to calculate from the bottom up. We need to use the array to store the values. This top down is very simple, very easy to understand, right? Yeah. And then the advantage of using this is that the computer takes care of most details. When the n and m is out of boundary and then it handles the cache, we don't need to particularly tell the computer how to remember the values. It's just like, okay, we ask computer to remember this value when you see it the first time. You remember it. Magic keyword, cache.
Yeah, without cache.
Without cache, bottom up. Okay. Define C and M. Again, there are 3 edge cases value. When m is bigger than n, return 0. If m equal 0 or m equal n, then return 1. We have to store the value in an array. Let's say dp array. dp equals, at the beginning we store it as a 0 times, look at the values here, Pascal triangle. So this is n rows. Here we want to have m columns. We need to create a 2-dimensional array times m for underscore in range n. Look, these values we know. We don't need to calculate. This is the boundary value. This is the boundary value, right? For I in range. Look at that. Let's say this is the first one is the 0 and the last one is n. So actually this is m plus 1 and m plus 1. The row number from 0 to m plus 1. So we want to prefill this column, which is dp I0 equals 1. Right? And this value we need to do it as well. So for I in range n plus 1. Right? So dp I equals 1. So we are filling these values. And then we need to calculate. For I in range from second row actually to n plus 1. for j in range second column to I, but this I could be bigger than the m, so we have to get a minimum. I and then m dp ij equals dp I minus 1, okay, I minus 1 j plus dp I minus 1 j minus 1, and return dp minus 1 minus 1. Minus 1, the index minus 1 is the last value, right? So basically this is the same as dp and m.
What you doing?
We need to fill the triangle. Each number is the sum of the two numbers above it, right? This is the way it is. So the j, the inner loop, the index will be going from 1 to the end, but not including this one. This one is 1, right? So which we have completed here. Okay. So as you can see, if we write it in bottom up, it will be non-trivial. So it's difficult to get it right because of the boundaries. Because we are filling this metric ourselves. But using the top down, we don't have to worry about details. We don't need to worry about where to store the values. Here we store the value in the two-dimensional array. But in the previous version, where do the values store? We don't care. We just ask the computer to store it using the cache. The computer just store the cache somewhere, right? Store the value somewhere. But here we are telling the computer, we want to store the value in here. Then we have to do it ourselves. But the advantage of this one is that it's practically speaking, the implementation is a bit faster because there's no function call. Remember previous one, the top down, we have the recursion, calling itself, right? Calling itself. But here, we just calculating the Pascal triangle from the top to the bottom. When we calculate this value, the two values are already calculated above it, right? Look, when we calculate this value, 6, we calculate this value, which is 3 plus 3. These two values are already known. We don't need to go through from the top to the bottom in order to get these two values, am I right? Because we already store it here. Yes? This value is only based on the two values above it, right? There's no point to store these values. We don't need it, right? We can just use the one-dimensional array. Am I right? Look, every time I calculate the value, one value in the Pascal triangle, I only need two values, right? This value and this value. Any value, I only need two values. I don't need the values prior to it. That means that I don't need to store it. So in order to do this, we can have a one-dimensional array, which is this bit, and then 1, and every time we calculate it backwards. So this is the same, but with the dp, we just have to change it. dp equals, at the beginning, the first value, 1 plus 0 times m. Right? And then for I in range, how many rows is it? So they are n rows. How many times I have to iterate? So n plus 1, yeah. And then dp I will be 1. This is setting the right boundary. So remember, the Pascal triangle 1, 1, 1, 1, 1, 1, 1, 1. This dpi is setting these. For j in range I minus 1 till 0 minus 1, so I go from I backwards. Then dpj plus equal dpj minus 1. So this is basically saying dpi minus 1j plus dpi minus 1j minus 1. And then return dp, the last value, which is the same as dpm. The space, we only use one-dimensional array. And here we're using the two-dimensional array. Which one is better? Here, this array, we're only using one-dimensional array. This two-dimensional array. The space complexity here is OM. The space complexity here is OM times n. So which one is better? Which one is better? Yeah, this one is better. The time complexity, both the same, right? There are two loops, OM times n, okay? So this is the most optimum solution in terms of time and space. Okay, so what have you learned today?
Combination or detail.
Yeah, combination. Combination. On day 93, we talk about this combination actually. This is a bit more details here, right? We're using the bottom up. These two are bottom up. The previous one is top down with the cache recursion with the memoization, remember? And then the formula, CNM equals n factorial divided by n factorial divided by n minus m factorial. Right? Okay. Okay, that's it for today. Bye bye.
Um,
Bye bye.